So first, quickly, the setting we are taking. We are, say, in a general setting of second-order elliptic uniformly elliptic second-order operators, which may be either in divergence, general divergence form, or general non-divergence form. Okay, so be it that or that. We are going to treat these simultaneously, or we may even consider fully nonlinear operators of AGB type. For instance, an extremal operator of Pucci type, which has that form. So yeah, so essentially what you may remember from this is that we are taking general form operators being in divergence or non-divergence form. And as for notations, it's good to keep in mind that B will stand for a first order coefficient and C will always stand for zero order coefficient in the operator. This one, the ellipticity constants. We consider at all times weak solutions of equations which contain such operators in the natural weak sense, that is weak Sobolev if the operator is in divergence form, solutions in H1 log, or viscosity, in this case LQ viscosity solutions if the operator is in non-divergence form. Okay. And yeah, the hypothesis we are making, so we are having a uniform elliptic operator, and the lower order coefficients which we consider are supposed to belong locally to Lebesgue spaces, which are the right framework for such solutions of such equations and inequations to satisfy generalized maximum principle, that is Stampacchia inequality in the divergence case, or Alexandrov-Wackermann-Pucci inequality in the non-divergence case, and the Harnack inequality. That is, in this situation, they are to be in the first order coefficient is to be in LQ for some Q bigger than N, and the zero order coefficient is to be in LP for some P bigger than N over 2 in the divergence case, and for say bigger than N, or bigger or equal than N, or bigger or equal than a constant which is known to exist and is between N over 2 and N, called the Escuriadze constant in the case of non-divergence operators. This is really what's the, let's say, right setting for such, for maximum principle techniques to apply. Okay, so since it is a broad audience, I'm gonna recall some very standard results in the theory of elliptic PDEs, and starting with the so-called strong maximum principle, which is generally taught to us as a linear result, saying exactly what's written here, that if we have a nonlinear super solution which vanishes in one point, then it vanishes everywhere. In the linear case, this is equivalent, of course, to saying that if a subsolution touches a super solution from below, then these two, they have to coincide. All right, this is the strong maximum principle, absolutely fundamental result. Discovery made by Vázquez almost 40 years ago is that actually the zero order dependence in the operator may be non-Lipschitz at zero. So we can have, for instance, a thing like that, a portion of U and a zero order term, which is some f of U, which is not exactly Lipschitz at zero, which is a bit worse. And to introduce what this worse means, so let's look again at the strong maximum principle. It is something very trivial, say for concave functions, right? If we take a concave function which attains a minimum, then it is constant, trivial. Then, okay, that's the beauty of elliptic PDEs, right? That many things which come from concavity convexity carry over to just elliptic PDEs. And here, for instance, we don't need the second derivative to be negative to have such a result. It's enough that the trace of the second derivative be negative, which means that there is more, the sum of the second derivative is negative. There is more concavity in the concave directions than convexity in the convex directions. And that's enough to say that if a minimum is attained, then the function is again a constant. Okay, adding lower order terms, well, how can we see that? For instance, adding lower order terms of term of U. This means that we actually don't need to have a negative trace of the second derivative. We may have a positive function which attains a minimum zero at a point. And the strong maximum principle says that for such a function, you cannot put under it it's hash, it's Laplacian. Still, it's impossible, except of course the function is constant again, right? There's no place under the function to put its Laplacian if it attains a minimum zero at a point. And okay, that's somehow also, there is a sort of a sharp threshold here, because if you try to increase this u like a power, this is no longer true. If you take Laplacian of, if you ask if the same thing is true, if you take a power which is strictly smaller than 1 here, know that u to the p is now much bigger than u, right? Because u is small around its minimum zero, then this is not true. I mean, it is simple to see that there are functions which even satisfy the equality here. They are just powers bigger than 2, classical solutions, which disprove the strong maximum principle for such an inequality. And the result of Vázquez says that the threshold here is strictly between u and u to the p for p bigger than p smaller than 1. And more specifically, it says that the following is true. If we have a, say, a positive non-decreasing function which vanishes at 0, then the strong maximum principle is valid if 1 over square root of the primitive of this nonlinearity f of u is divergent at 0, right? Is not integrable at 0. Right? Then, under this hypothesis, it is true that, of course, obviously, this hypothesis is log of s at 0 is infinity if we take a linear f here. And the main example is the following, that if this hypothesis is satisfied by functions which grow like s times log s to a power which is may go up to 2. And this is really the essential growth that you may expect for functions f here, such that, as I said, strictly between s and s to the p for p smaller than 1. Right, that's the example. And in particular, important situations which pop up is the case in particular a equal to 1 here, of course, and a equal to 2 also in some geometry problems. Just a remark, you may have seen such a hypothesis in other situations. It's indeed somewhat, not exactly related, but due in a way to the integral condition obtained by Keller and Osserman for existence of entire solutions. But there, this divergent integral is at infinity, actually. Right. Okay, so starting from that, from the result of Vázquez, there's been really a huge work of extending this sort of strong maximum principle to weak solutions and all sorts of more general operators, be it quasi-linear, fully nonlinear, singular, degenerate, such as of P-Laplacian type. To give a reference, there is a nowadays already very well-known book by Patricia Pucci and James Sarin, which is almost entirely devoted to this result and to the maximum principle in general, but it's centered on this type of results. And it considers really very general operators of, say, pure Laplacian type. A thing they also show is that the integral condition, the Vázquez integral condition, is also necessary, and that this non-decreasing hypothesis on f is enough to be assumed only in the right neighborhood of 0. And there have been recently some works which show that this latter thing can be removed in some cases. So for fully nonlinear operations, I refer to work by Felmer, Montenegro, and Quaz in 2009. We also had a paper with Felmer and Quaz somewhat related to that a little bit later. What is remarkable in all these works is that all of them require operators that have bounded coefficients. All these b's and c's and so on need to be bounded. And that's due to the method of proof. What's the method of proof? The method of proof is the standard, in a sense, not standard, but the proof that we essentially learn in an introductory course on PDEs of the strong maximum principle, right? That's let me recall that. So what's the standard proof of the strong maximum principle? Well, first you need to have an operator such that if it's 0 or the coefficients are nice, it satisfies the comparison principle. Then this is an essential step, you construct a radial subsolution in general in an annulus with, say, values to different constants on the boundary of the annulus, and a normal derivative of this subsolution which does not vanish on the boundary of the annulus. And this is enough to deduce the Hopf lemma, right? By precisely comparison between your super solution and that subsolution, because the super solution would have even larger normal derivative on the boundary. And then from the Hopf lemma, there is a well-known way to deduce the strong maximum principle, essentially using a continuity connectedness argument. So in this plan, the integral condition appears in the second step, right? When you want to precisely show that such a subsolution exists. The way it is done, it is to solve a boundary vary problem for an ODE, right? And that requires radial, of course, coefficients, and in general constant even. Simpler, but at least radial coefficients of the initial PD. So, for instance, to prove the Vázquez maximum principle for this equation here, what would you do? If B is bounded, you solve the equation where B is substituted by its minimum, and this already this is a constant coefficient equation. You solve the boundary volume problem with value 0, 1 at 2 different points. And then it turns out that the normal derivative of that solution, that is the derivative, the 1D solution, does not vanish on the boundary precisely if the integral condition, on Vázquez integral condition, is valid. So that's the way the standard proof works. So the point is that this, this does not seem to work if, for instance, here this B were unbounded. Yeah, right. There's no direct way of constructing a radial subsolution of that equation if, say, B is an unbounded function. And it appears that to date, such results were essentially unable, completely unable, in fact, as a matter of fact, for operators with unbounded coefficients. And that's our first result with Philippe. We settle the strong maximum. Of course, one would expect it to be true, right? Even for unbounded coefficients, provided they are not too bad so that in general, the operator itself is amenable to the maximum principle techniques, such as I said, for instance, B is in LQ for Q bigger than N. And that's exactly what we prove with Philippe under a supplementary hypothesis. So yeah, if we have a super solution and we assume that F, this nonlinearity, is as in that main example I gave for the Vázquez integral condition, that is assumed that F is no worse than, or more exactly, the derivative of F is no worse than log S to square at 0. Right? If F has a derivative which is not worse than log S to the square at 0, it can be infinity, but no more than log S to the square, then the strong maximum principle holds. I've written here essentially infimum in a bold to just because U may not be continuous, in particular if it is just an H1 function. But this, of course, means that if U is continuous, this is U is 0 at one point. And then we have that the strong maximum principle holds under this hypothesis here, which essentially covers all the cases in the main example. In this, what one most often encounters in the applications. And speaking of applications, I would like now to show you one, which is actually how I came to be aware of this problem and the lack of strong maximum principle of that sort for operators with unbounded coefficients. It's at first glance a very different type of problems, which are so-called elliptic problems with natural growth in the gradient. So just think of an elliptic operator, a linear elliptic operator, and there is a term which is quadratic in the gradient. I think, say, gradient u to the square times a function. I mean, this is actually an important class of equations. They appear in all sorts of applications. And there's been a really huge work on such equations and solvability of such problems, uniqueness of solutions or non-uniqueness of such problems, a priori bounds for solutions for such problems. I've quoted a little bit here in the so-called coercive and non-coercive case, which correspond to C having a good or bad sign. And in particular, for non-divergence operators, actually, they have been these equations for in the non-divergence scenario were studied quite recently itself, and in particular in a recent work with Gabriele Norberg, published a few years ago, in the non-coercive case for non-divergence form operators. We show that what's been known earlier for operators in divergence form, where more methods, more approaches are available for study of this problem, is valid also for non-divergence form operators. But the only way we found to prove that a crucial a priori bound for solutions of such equation is true was to actually reduce this sort of problem to the strong maximum principle for precisely that equation over here, u log u to power 1. And we realized that actually we did not know how to prove the strong maximum principle for that thing. And so in that work, all results are stated for operators with bounded coefficients, which is really not natural in that framework. You would expect to have B in LQ, C in LP. But our results were restricted to bounded coefficients because we didn't have a strong maximum principle for that. And for instance, the theorem that I just quoted with Philippe takes care of this, so it automatically extends all results on existence and a priori bounds for solutions of such equations to the cases of coefficients, of unbounded coefficients. All right, so a few more remarks. The method to which I'm coming now, the proof, absolutely does not see any monotonicity assumption of f, because there's no comparison with a given subsolution. So it automatically removes that assumption that was appearing in most of the previous works. And now, a first open problem, of course, would be that, okay, we prove under this hypothesis, can we replace this by the full Vázquez integral hypothesis here and still have unbounded coefficients? We do not know. I mean, it's, of course, one would expect it to be true, but that hypothesis is quite an ODE one, right? This integral hypothesis on the primitive of f. So how exactly, I'll come back to that. It's not completely clear if one could get the full result for unbounded coefficients, and that's an open problem. Well, a few work of the method of proof. Well, it's based on the Harnack inequality, or even more specifically, the weak Harnack inequality, and in which the constant in the Harnack inequality is optimized with respect to the domain and with respect to the norms of the coefficients of the operator. Okay, so let me recall you what is the weak Harnack inequality to start with. The weak Harnack inequality is a fundamental result in particular in the regularity theory for elliptic and parabolic PDEs, and it says the following: given a non-negative supersolution in, say, some domain, say a ball with radius r plus 1, then in any compact subset of this domain, taken here BR, you can bound some, say, epsilon norm of the function u by the minimum of u in that compact subset, multiplied by a constant, and that constant, here there are two constants, right, epsilon and dc. Epsilon depends on the ellipticity and the dimension. Actually, for divergence form operators, it depends only on the dimension and is known. It's n over n minus 2. And this constant here depends, again, on the ellipticity, dimension, the PQ, these LP-LQ spaces, and the norms of the coefficients, the low order coefficients, and the size of the domain. Right, so that's the optimization is with respect to these quantities, which need to be made a little bit more precise too here. I didn't write exactly what is this Q and P here, but the optimization is done with respect to these. Well, that's really a result which is very well known. For divergence form operators, it goes back to De Giorgi, Moser, and Trudinger. For divergence form to Krivov, Safonov, Caffarelli, Koike-Swish. In this generality, it's due to Trudinger in the divergence case and to Koike and Swish in the non-divergence case. It's a quantification of the strong maximum principle, right? So if this is 0 here, automatically this is 0, so U is 0, right? And it's a growth lemma. It tells you that if U is bigger than some constant on a measurable subset of BR, then U is bigger than a small but still positive constant on OBR. That's what it says. That's a growth lemma, and as such, implies the solutions are held regular through a known procedure. Well, it's really a basis for the regularity. And there is also a non-homogeneous version of that, where you need to add some norm of F in the LP norm of F, if there is a right-hand side. I should have, that's actually not very good notation. I should have taken another, no, this is not the F from before. This thing, it's a H of X, some function of X here in that inequality. And that's a confusing notation. This is just a function of of X in the right-hand side here. And we get that. So what we want to do is, in that inequality, optimize a little bit a few things. First, one thing, before speaking of the constants, what the constant is the most important, of course, but another thing that we actually need to optimize in particular for the Landis result later is also this dependence here. See, that's the usual form in which this inequality is given. And in a sense, it's strange because you don't get the result for bounded F as a limit as P goes to infinity for unbounded Fs, right? Because if F is even a constant here, then its L infinity norm is independent of R, of course, but if its LP norm increases when the domain increases. So first, we take care a little bit of this thing, obtaining a more precise result, which tracks only how F behaves locally, and which does not depend on the expansion of this domain here when R goes to infinity. And as for the constant, we are going to optimize it with respect to norms of R, with respect to R, and norms of B and C, exactly in the same sense to only local norms, which see the behavior of B and C as well only locally, do not without depending on the expansion of the domain. Okay, so to do that, we use uniformly local Lebesgue spaces. This is actually well known to in particular in study of parabolic equations. So the uniformly local Lebesgue space is simply you take the norm of the function to be the maximum of the norm in any point in your domain intersection with a bow with radius 1. So this is only locally. This doesn't get worse necessarily if omega gets bigger. And then define the following. For any number bigger than n, define the constants 1 over minus n over r and 1 over 2 minus n over r. And in particular, if r is infinity, get beta to be 1 and gamma to be 1/2 n. And the following quantity, the norm of B in the LQ norm uniformly local only to a power beta Q with R equal to Q, and C2 with power equal to gamma of P. So if P and Q are infinity in particular, we get here B to power 1 and C square root, which is the best, as you can expect, for then the Harnack inequality. The optimized Harnack inequality tells you that the constant in that thing over here is actually controlled by an exponential a times r. Note a depends on r, but only through this thing here, and the norm is Volkov's here. So it's really like e to the power of r times a, where a is that quantity. And of course, this is optimal, as you can immediately see, just taking an ODE. Say, if you take this ODE, its solutions are exactly exponential of the size of the domain times b times times square root of c, right? So that's optimal. But it so happens that this is true for general elliptic operators. Okay. Okay, I'm not going to bother you too much with proofs, but I mean, for each of the proofs here, you need to pull out a few tricks, but actually understand why the results are true is really not difficult. And I'm going to keep to just giving a few ideas. So what's the idea of proof that? Okay, given this A, take a bow of size, which is size a to power 1 over a, rescale that bow to a bow of size 1. Then you get a new operator in a bow of size 1, whose coefficients have norm, which are bounded by 1. So the standard weak Harnack inequality gives you a constant, which now does not depend on any lower order terms, right? Then you can scale back and cover the domain with overlapping bows of this size. And again, use a Harnack chain. You have to do it right because there's the integrals here, but use a Harnack chain, which again is optimized with respect to the geometry of the domain. And it gets you a constant like that in the end, after doing the work. Yep. Also, let me observe that we have a Volkow maximum principle. This is even easier to get. This is the other inequality here, right? When you get to bound the maximum of the function by a constant times norms of the function in the right-hand side, right? And actually, in the Volkow maximum principle, the constant is even way better than here. It's not exponential in A, it is a polynomial in A. So when you join together these two things, you get the full Harnack inequality, again with a constant of this sort. And now a very quick explanation why actually this weak Harnack inequality gives you a proof of the Vázquez maximum principle now. And that's the way you prove it. Okay, think of our equation, and now the zero order operator, let's imagine the zero order coefficient is, say, some log of u. Well, you cannot exactly do that because it's unbounded and you don't know how u behaves, but let's imagine for an instant. And then you have an inequality of this sort. And this C here, this A here is like, let's say, imagine it was bounded, even if it is not. It's like square root of C, square root of log of u to at most 2, right? So in this inequality here, at the point where you around the point where u attains minimum, this is of order 0, of order u and 0, and this is infinity. And if this behaves well, this is not a worse infinity than the 0 here. And so in the end, after some work, you do prove that u indeed is identically 0 if r is, say, sufficiently small. So that's the essential idea of the proof here. This infinity times 0 here is a controlled indetermination. Now, another question that really remains here, and I would like to point out is, okay, we prove a strong maximum principle specifically for the nonlinear operator, but we use a Harnack inequality or a weak Harnack inequality for the linear equation, essentially. So one may ask, would there be a direct Harnack inequality or weak Harnack inequality for the nonlinear inequality, in which, of course, this Harnack inequality would be a nonlinear, the dependence in a super view or a normal view or the info view would be nonlinear. instead of linear as it is for the linear Harnack inequality. And it's actually true in a very particular case, as was proved by Vese-Yulin in 2016. In particular, if you take a pure second order operators, no zero order terms, and the divergence structure necessarily, and then it is indeed true, there's a very exact Harnack inequality, which tells you that you have the integral from inf u to sup u of 1 over square root of the primitive of this is bounded by something which is completely independent of f. Of course, if f is 0, this is the usual Harnack, right? Log of sup u over nf u is bounded. The proof is difficult, uses the divergence structure, uses the Denebet-Trudingier approach, which is consisting writing an ODE for the volumes of super-level sets of solutions. Would be interesting, to, of course, very interesting to ask whether such a result can be proved, or at least something like this could be proved for general second-order operators, say Pucci, say second-order operators in divergence form. By some, probably would need some iteration. I mean, a sort of a Krylov-Sifonov Caffarelli iteration, but done so carefully that it sees the fact that in F, in each step of the iteration, that log term will get things worse, but in the end, the iteration would converge because the log is not too bad. That's another open problem. Okay. So now let me move to the second question that we study through Harnack inequality with an optimized constant. It's the so-called Landis conjecture. That's a question by Kondratiev and Landis in 1988. Since it's called the Landis conjecture, I assume that actually people were working, probably starting with Landis himself, much earlier than that on this problem. I don't know that if everybody knows who is Landis, by the way. Evgeny Landis was a Soviet mathematician who, of the 60s to 80s in the last century. And I suppose everybody's heard of Krylov and Safonov and their regularity theory. One may say that Krylov and Safonov went to the end of the road that Landis opened. So he really has had some important contributions. Kondratiev is another important Soviet mathematician and specialist on qualitative properties of solutions of PDEs. And so it's an extremely simple question. I mean, it's a super simple question. Just take, say, Schrodinger operator, Laplacian plus a zero order term, bound it in, say, exterior domain. And is it true that solutions of such a thing cannot decay super exponentially at infinity? In other words, or more precisely, can we find a constant which would depend, say, only on a bound of this C of x, such that if u goes more quickly to 0 at infinity than exponential minus Cx, then u is actually the trivial solution. It so happens that this question was asked more than 30 years ago, and the result is practically, it's still open for real solutions of equations like that. Originally, it was asked in R2 also for complex solutions. And actually, the result was, the question was quickly answered in the complex case. And it happens that, that's already a first thing that, first indication that it's really a difficult problem, even though it's so simple to state. I mean, at first glance, you may think it's unbelievable. It can be that hard. Is that in the complex case, the Landis conjecture is false. I mean, if you take complex solutions of this thing, if you admit complex solutions of these things, yeah. Before moving to the complex case, I have there are of course variants of that questions. Let me mention a few of them. The question is still unanswered even if the solutions are entire. I mean, if the equation is given in ORN, it's still open. 2, there's a weaker conjecture by Harnack, which says that solutions cannot decay quicker than exponential to x to a power bigger than 1. This is also still open in dimensions bigger than 2. And of course, one may wonder, what about more general operators than just the Laplacian here, right? So as I was saying, the original question was answered a few years after it was asked by Meshkov. And it turns out that if complex solutions in R2 are admitted, then the result is false. And the optimal rate of decay is minus x to a power 4/3. This has been a question which has been studied in a number of papers by Bogan, Harnack, Escuriaza, Pons, Vega, Davies. These authors have worked a lot on this. And through Karleman type estimates, one proves these sorts of results for much more general equations and situations. Okay, since these do not distinguish between real and complex solutions, they are really like, they cannot, there's no hope to give an answer on the real conjecture, just real solutions here by such techniques. But in any case, in the complex case, the conjecture is false, and that's all it's known actually, let's say, as a full answer in some situation. Now, moving to the real conjecture, to admitting real operators with real coefficients and real solutions, which is what we are interested in. There was a paper which quickly became known by Harnack with Silvestri and Wang in 2015, where they proved the quantitative bound in 2 dimensions for operators in divergence form, and some more coefficient and some more hypotheses, where they proved that in Rn, essentially the decay can be no worse than R log R when you take, say, that is X log X, right? Modulus of X log modulus of X. And for exterior domains, X log X to the square. There's been a number of generalization by, in particular, Harnack people in the Harnack school. And this works for divergence form operators and dimension 2, and make the essential hypothesis, and that's really a hypothesis which seems to be very hard to go away from, is that the equation, the operator is such that it satisfies the maximum principle on bounded subdomains of the given domain. Which, in other words, if you are familiar with this terminology, would be to say that the generalized first eigenvalue of the operator in the domain is non-negative. All right. So that hypothesis appears in all works apart from one, and I'll come to that up to now. Now, for operators in Rn, Vuka-Rossi recently proved that non-divergence form linear operators with bounded coefficients have the Landis property, in the sense that one may find a C where C depends on bounds of the coefficients, provided again we have the condition on the first eigenvalue of the operator, right? And also exterior domains can be considered, provided one assumes a sign condition on the solutions on the boundary. Now that works uses a comparison and some sort of comparison between the given solution U and a subsolution here, which is exponential of m to x and for some very big m. And it is possible to find such a subsolution precisely because one assumes an operator with bounded coefficients here. There are also some earlier works in the same line by probability techniques, and also work by Lebauc by a duality method of Michel Pierre, which leads to results which are similar some situation even more precise, a little bit more precise, such as this one. So the question is essentially settled, let's say, in non-divergence case for operators with bounded coefficients, provided we have this strong assumption here, well, somewhat strong assumption here satisfied. And now, very recently, I mean, this is the first time someone has gone beyond the assumption on the maximum principle. See, this assumption is essentially also an assumption on that tells you that the zero order coefficient dc of x cannot be too positive, right? And it was completely removed very recently in a difficult paper by Logunov, Malenikov, Nadirashvili, and Nazarov, which proves in 2 dimensions only the Koenig's form of the conjecture, or more precisely, it says that, well, we can say that the word decay at infinity in general can be no worse than x times square root of log x. This uses really 2D techniques. Higher dimensions continue being open if we do not assume anything on the maximum principal properties of the operator. Now, as far as unbounded, all this up to now was more or less about bounded coefficients. For unbounded coefficients, there's been a few works again in 2 dimensions and divergence form operators, but they are in a sense a little bit different in that the coefficients are assumed to be integrable at infinity, at the NLQ of the whole space, and there is a growth assumption on U, which is not exactly x to the x, but x to the x to a power smaller than 1. And these hypotheses lead to a different Landis type result, which is a stronger conclusion, which tells you that the solutions cannot decay even more than exponential of minus x to a power which is smaller than 1. Right. So our contribution is actually simply to more or less to prove that the results of Rossi and here can be completely extended to operators with an unbounded coefficients and through a different technique based on the Harnack inequality. And that's what we do. We prove the Landis conjecture in any dimension for any unbounded order of the coefficients, which are only uniformly locally integrable. Thus, bounded coefficients become a particular case. And again, we have the hypothesis that the maximum principle holds in any bounded subdomain. We have no idea how this could be removed. Exterior domains can be considered too under a sign condition on the boundary. More precisely, we have the following theorem. Given operator in any form, divergence or non-divergence, assuming that it satisfies the maximum principle on bounded subdomains, we can find a uniform constant such that if we have a solution of this in Rn or in any exterior domain with a sign condition on the boundary, then we can prove that you cannot decay worse than an exponential of minus constant times x, and the constant can be quantified with respect to the law or the coefficients of the operator, which, as I said, functions which are only locally integrable in omega. Okay, so that's the result, and a quick view on the proof. So how does it work? One, since the maximum principle in bounded subdomains is satisfied, one can construct a signed solution of the equation in the whole domain. Now, this having a sign can be subjected to the sharp Harnack inequality that we already have. And that sharp Harnack inequality tells you that this solution decays at most exponentially at infinity. So if you decay it quicker, you can use comparison to squash U with psi. So that is, you can apply to a comparison principle to U, and any small constant times psi in a sufficiently large ball. But since this delta is arbitrary, you can essentially end up with u being 0. It's really, that's the idea of proof of this theorem. Again, you need some work to do to make this work, but essentially the idea is quite simple to grasp. Well, now to move to a conclusion. So we have a new approach based on the Harnack inequality with a sharp constant, which unifies the treatment of these two different problems, which previously were never actually connected in any way. And it has this treatment has the following advantages. It lets you consider operators with unbounded coefficients in a number of cases, situations, for a number of problems where all previous results required bounded ingredients. For the one-disk conjecture, actually, it extends many results even for bounded coefficients. For instance, one-disk conjecture was never considered for equations, for fully nonlinear equations. And these methods, of course, it's just never sees if it is exactly the equation. It uses only Harnack inequality, which is valid for such equations. And it treats simultaneously equations in divergence and non-divergence form, since the Harnack inequality is a common fact for such operators, right? So that's to conclude, that's essentially what's done in this work. And thank you very much for listening.